When working in geometry, and even classes prior to that, a lot of times you were taught that the formula for finding the area of a triangle is that the area is equal to 1/2 the base times the height. And I think it's misspoken because actually that's only one of several different formulas for the area of a triangle. There are many more that would be applicable to different types of triangles depending on what information you know about the triangle. So yes, if we know one of the sides and we know the length of the altitude to that particular side, I can find the area of the triangle using that formula that it's 1/2 the base times the height. But there's a lot of situations in applications where that's not the information we know, and it's not easy to get to that information. So what this video does is to present some other formulas for finding areas of triangles dependent on what information you know. So I'm going to first go over the different formulas and then we'll do several examples. So if you do know one of the sides and the length of the altitude to that side, then you will want to use that the area is equal to 1/2 the base times the height. Now, I actually use K throughout this for the symbol for area, and you'll find that a lot of times in your trig books they'll also use K. The reason is some of the other formulas are going back to the convention that we're going to denote our angles by capital A, capital B, capital C, and our sides that are opposite those angles with the matching letters that are small case. So I'm already using capital A for an angle name. I can't also use it for the area denotation, or else it's just going to get too confusing within the formulas. So here we're going to always use K for our area so that we don't get it confused with angle A. So our area of our triangle is 1/2 the base times the height when you know one of the sides and you know the length of the altitude to that side. Now, what if you have the information where it's side, angle, side? So remember with side, angle, side, as we're coming from information we don't know around the triangle to information that we do know, then I would know a side, I would know the angle, and then I'd know another side right away. That would be your side, angle, side. And let's just draw a triangle like that for now so that we can kind of see what we have. So we're just going to draw a triangle with our A, B, C for our angle names. And across from angle A is side A, across from angle C is side C, and across from angle B is side B. So if I know side A, and I know angle C, and I know side B, I'm going to have two small case letters for the two sides I know, and a capital letter for the angle I know. And none of the letters are going to be the same as each other if I have the side, angle, side case. So notice, side, small case A, angle, capital C, side, small case B. And even if I went around the triangle with side, angle, side, it would be the same sort of situation that we would have. So if we had side, angle, side this way, it would be side B, angle A, side C. So if that's the information that I have, then my area formula is equal to 1/2, so the 1/2 is still in there, times A times B times the sine of angle C. So you've got two sides and you've got an angle. None of the letters match when you have the side, angle, side case, and it's going to have that 1/2 like we've had with the other formula for the area of a triangle. And then I multiply the two sides that I have times the 1/2 and then times the sine of the angle that I have. Now I just did one form of it here, but if you had the other pieces as you went around the triangle, for example, if I did have side C, angle A, side C, then I would have 1/2 B, C, sine A, and then whichever rotation you have. Next, what if we have angle, side, angle, or angle, angle, side? Well, for angle, side, angle, or angle, angle, side, as you're coming from the information you don't know around to the information you do know. So like I would have angle C, side B, angle A, that would be angle, side, angle. So notice I have two capitals and a small case, and for angle, side, angle, none of my letters match either. But there's two capitals and a small case instead of two small case and a capital. Now, in a triangle, I know that the total of the three angles add up to 180 degrees. So if I know two of the three angles, I can get the third really quickly by just taking 180 degrees and subtracting the sum of the two angles I know. So I could also look at this that if I have angle, angle, side, that I could go ahead and find that third angle and then transition that into an angle, side, angle. Now when you've got that information, your area formula is equal to, and this really had a 1/2 multiplied out in front of it, but to make it look a little bit more simplified, that 1/2 multiplied in front of it just ended up as a coefficient of 2 in the denominator. Then the only side you have is squared, and it's multiplied to the sine of the two angles that don't match that letter. So here it's k is equal to a squared times the sine of angle B, the sine of angle C, and then in the denominator we've got that 2 because of the 1/2 coefficient, and then the sine of the angle that's opposite the side that you know. So the rotations around for this, our first one is k is equal to a squared sine angle B sine angle C divided by 2 sine angles A. If I had B squared up here, it would be sine of angle A sine of angle C divided by 2 times the sine of angle B. So that's how it just kind of works around. Now, what if you have side, side, side? So if you have side, 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 always remember that the addition of the smaller two lengths of the sides, those smaller side lengths added together, always has to be a number bigger than the longest side, or it doesn't make a triangle. So you always want to check and make sure that that's true. But then after you check and make sure that that's true, you first find what's called the semiperimeter. And the semiperimeter is just halfway around the outside perimeter of the triangle. So you add the three sides together and divide by 2 to get what's called S, the semiperimeter. And then your area is equal to the square root of S times S minus A times S minus B times S minus C. And then you would want to simplify that radical as far as you can simplify it using the rules of radicals. If it asks you to approximate it, definitely you would want to do that. If it doesn't ask you to approximate it, you should always give your exact answer with the radical still there if it doesn't completely simplify out, and then an approximation just to be on the safe side with it. Now another situation that could occur is if we have our side-side angle case. And remember, the side-side angle case was the ambiguous case. If you don't recall what the ambiguous case means or how to determine that, I have a couple of videos actually on working with the ambiguous case, and I've copied the links to those videos in the description of this video. So with the ambiguous case, depending on whether you have an acute angle or an obtuse angle, and then the relationships of the lengths of the sides opposite and adjacent would determine whether you get one triangle or two triangles or maybe no triangle at all. And how you know with your situation of whether it's the ambiguous case, it's two sides and an angle. So you're going to have two small case letters and a capital letter. And then one of the side letters is going to match the letter of the angle. And when that happens, you know that you have the ambiguous case and you need to really be careful with it. Now, you'll determine which case you have. Once you determine which case you have, either you don't have a triangle and you just say it doesn't make a triangle, so I can't find an area, If it does make a triangle, then you go ahead and find the area after using the law of sines to get another side and turn it into a side angle side case and use the area for our side angle side, the 1/2 AB sine C. Now, if you've determined from working this that you've gotten 2 triangles out of it, you need to solve for both triangles and give the area of each of the triangles to actually completely and accurately answer that question. So now what I'm going to do is to erase and reorganize this a bit and do a few examples for you. Okay, so here I have 3 different examples to work for you. The first one says, and this is find the area for all of them, but the first one says that B is equal to 127 degrees, A is equal to 32 inches, and C is equal to 25 inches. So when I look at this, I see that I have 2 side lengths, and I see that they're small case, but also they're measured in inches, so I know that they're the sides. So I have 2 side lengths, and then I have a degree measurement for my angle. So I do know I have 2 sides and an angle. I just don't know if I have side angle side or side angle. Let's see what it is when we draw it out in our triangle. So I have my angle B is 127 degrees. The side opposite angle B is side B. Then I have angle A, and the side opposite A is side A. And I know that side A is 32 inches. And then my angle C, and the side opposite angle C is side C. And side C is 25 inches. So now when I go around from information I don't know towards the cluster of the information that I do know, and I say the entity of the triangle it is by what it is that has the measurement on it. So coming around, I know a side, I know an angle, and I know a side before I get where I don't know information again. So this is side, angle, side. So remember with side, angle, side, you get a triangle. So I can go ahead and just determine which of these formulas that I should use. And for side, angle, side, we use the formula K is equal to 1/2. The 2 sides multiplied together times the sine of the angle that's between them. So here I have my side A and my side C. So my K is equal to 1/2 AC sine B. So just a different, like said, of the lettering that we have on the triangle. So we're going to have K is equal to 1/2. A is 32 inches. C is 25 inches. And then times the sine of angle B, which is 127 degrees. And when you multiply these out, you get approximately 319 square inches. Remember, inches, units of measure act a lot like variables do. So if you're multiplying inch times inch, you get inch squared. So square inches is what we say. And you would want to check with the situation that you're working with how you would determine your rounding and what the person that you're reporting to would request as the rounding. Since our sides are all with 2 significant figures, I'm going to report this with 2 significant figures. So my area is approximately equal to 320 square inches. How about problem 2? Well, problem 2, I have angle B is 42.8 degrees, angle C is 76.3 degrees, and side C is 17.9 meters. So I only have one side, and I have 2 angles. And I know that in a triangle I have a total of 180 degrees between all 3 of the angles. So knowing two of the angles, I can use that information to get the third angle. So then angle A is 180 degrees minus the sum of these two angles. So I am going to get 119.1 degrees. So that's my angle A. And now I have three angles and a side. So with three angles and a side, I'm going to use this formula. And again, I could look at seeing which of these pieces of information I have for which case it is. So if I have my angle B is 42.8 degrees and my angle C is 76.3 degrees, then we found our angle A to be 60.9 degrees. The side opposite the angles have that small case letter name. So this is my side A, this is my side B, and this is my side C, which is the 17.9 meters. So my original information that I had was B and C and side C. So as I come from information I don't know around to information I do know, I hit an angle I know, and then I don't know that side, so I can't say side. And then I hit an angle that I know, so that's angle, angle, and then I hit a side that I know. So this is angle, angle, side that we have for the case that we would use. But either angle, angle, side, or angle, side, angle, we use that formula. So now my area is equal to the side that I know squared, so 17.9 meters squared. Now I'm going to multiply by the sign of the angles that don't match that letter. So here, this was the side C. I'm going to multiply the sign of angle B and angle A in the top. So I have times the sine of 42.8 degrees times the sine of 60.9 degrees, and that's divided by 2 times the sine of the angle that matches the letter of the side you know. I know side C, so the sine of angle C is what goes in the denominator. Now, when I go through and work that all out, and I get my approximate value, and then I look, my sides are to 3 significant figures because my angles were to the nearest tenth. And if you need to review significant figures, I also have a link to a significant figure video in the description of this video. But I'm going to here again report this to match the number of significant digits for the length of the side when I report the area. So I'm going to do it with 3 significant figures, and it's approximately 97.9 square meters, because meter squared gives me square meters. So that's the area for that case. Now let's look at our third example. Our third example is side A is 32 meters, side B is 24 meters, and side C is 36 meters. So here I have side, side, side. There's no angles given at all. So with side, 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 we are going to use this formula. And it's actually called Heron's formula after a mathematician that did a lot of work that was from Alexandria. Historians actually believe Archimedes was the one that kind of developed the formula, but Heron was one that gave a really great proof for it, and his name associated with it kind of has stuck. So with this, the first thing we need to do is find our semiperimeter. So we're going to take our 32 meters plus our 24 meters plus our 36 meters and divide that whole thing by 2. And that's going to give us 46 meters. Now our area is the square root of, and I have 46 meters for S times S, which is 46 meters, minus A, 32 meters, times 46 meters minus B, minus the 24 meters, and then finally times 46 meters minus the 36 meters. Now, one thing that I didn't stop to do, I know it's true, but I should have mentioned it, is I look at all these three sides. 32 and 24 are both numbers that are less than 36. So the 32 and the 24 are the smaller sides. The 36 is the length of the longest side. When I add these together, I get 56, which is bigger than 36. So I know I have a triangle. All right, now when you go through, work what's inside the parentheses first. So K is equal to the square root of 46 meters times, and then 46 meters minus 32 meters gives me 14 meters. Then times, we're going to have 22 meters, and times 10 meters. And then multiplying these all together and looking at simplifying them, meter times meter times meter times meter is meter to the fourth power under a square root, but the square root of your meter to the fourth gives me meter squared. And when we give our approximation is about 380 square meters. Looking at the fact that these are all given to two significant figures, so I'm going to round that to two significant figures. Now, if we are looking at also wanting to make sure that we give the answer exact with the radical, I know the meter squared comes out, and when I look at each of these, 2 goes into 46 and 2 goes into 14. So we can kind of look at factoring these out. I'm actually going to give myself a little bit more room by going underneath here. So 46 is 2 times 23. 14 is 2 times 7. 22 is 2 times 11. And 10 is 2 times 5. So every pair of identical factors under the radical comes out with that number outside the radical. So I have a pair of 2's, so a 2 will come out, and another pair of 2's, so another 2 will come out. So I'll have a 4 in the front of the radical, and then 23 is prime, 7 is prime, 11 is prime, and 5 is prime. So I can write this as K is equal to 4 times the sum of 8,855, and that's square meters. So here's my exact value, and here's my approximate value. And again, you want to find out from who you're doing the reporting to, which way they would like you to leave the answer. So hopefully you've been able to follow along and to see that there are a lot more situations with triangles and finding the area of triangles than you were led to believe when you were in your geometry course or even just in classes prior to that. Main reason is you have to wait till trig to get the other formulas that involve the trig functions, and you have to wait until you know how to work with radicals before you can do the one that's Heron's formula. But I guess what I'd like to see is maybe saying a formula for the area of a triangle is such and such when you're being introduced to it originally, and then possibly saying as you learn more mathematics, you'll find there are more formulas for the area of a triangle, but right now we're just sticking with the one that we have the background to do.